after you take differential equations so that you know how to solve the differential equations. But we're going to write down the solution in particular here for E, the binding energies of the electrons to the nucleus. Okay? So we've got H psi equal E psi. And when we solve that equation, we get the following expression for E, these binding energies. E is equal to 1 over n squared times m e to the 4th over 8 epsilon naught squared times h squared. All right? That's what we get out of it, and there's a minus sign up in front. Now, m. What's m? M is the mass of the electron. What's E? E is the charge on the electron. Epsilon naught? Well, epsilon naught is this permittivity of vacuum that we talked about before. It's really just a unit conversion factor here. H, Planck's constant. Here comes Planck's constant again. It is ubiquitous. It's everywhere. Okay? And what we do is that we typically take all of these constants and group them together, okay, into another constant that we call the Rydberg constant. And we denote it as a capital R sub capital H. So all of that is equal to R sub H. So this is over n squared minus 1. All right? And the value of R sub H, that Rydberg's constant, and this is something you're going to need to use a lot in the next few weeks, is 2.17987 times 10 to the minus 18 joules. All right? All right. But you also see in this expression for the binding energies of the electron to the nucleus that there's this n here. What's n? N's an integer. When you solve that differential equation, you find that n has only certain allowed values. Right? N can be as low as 1, 2, 3, and hey, n can go all the way up to infinity. N is what we call the principal quantum number. All right, I'm going to explain that a little bit more by looking right now at an energy level diagram. So that's the expression, but now let's plot it out. All right, so we're going to be plotting this expression as n goes from 1 to infinity. So I have the energy axis here. Energy is going to be going up in that direction, up. So when n is equal to 1, well, when n's equal to 1, the binding energy of that electron to the nucleus is effectively the Rydberg constant. Here I rounded it off, 2.180 minus 2.180 times 10 to the minus 18 joules. But our expression here says that there can be another binding energy of the electron to the nucleus. It says that n can be equal to 2. And if n is equal to 2, well, then the energy, the binding energy of the electron is a quarter of the Rydberg constant, right? Because it's a Rydberg constant over 2 squared. If n is equal to 3, well, our expression says that the binding energy is minus a ninth of the Rydberg constant. If n is equal to 4, it's minus a 16th of the Rydberg constant. N equals 5, minus 1/25. N equals 6, minus 1/36. N equals 7, minus 1/49. All the way up to n equal infinity. And you know what the value of the binding energy is when n is equal to infinity? 0. Okay. So our equation says that the electron can be bound to the hydrogen, to the nucleus with this much energy, or this much energy, or this much energy, and so on. But it can't be bound to the nucleus with this much energy, somewhere in between, or this much energy, or that much energy. It has to be exactly this, exactly this, exactly this, exactly this, or so on and so forth. Okay? That's important. What we see here is that the energies, the binding energies of the electron to the nucleus are quantized, right? That binding energy can only have specific allowed values, right? It doesn't have a continuum of values for the binding energy. Yes?
In the Schrodinger's equation, H psi equals E psi, are those the same size?
Those are identically the same size, but remember, no, remember, because this is an operator, right? I left the hat off here. Remember, that was we took a second derivative of psi, okay? So you can't cancel this. This is an operator taking the derivative of psi, all right? So you can't just cancel that. This isn't a multiply by on this side. This side is, right? This is E times psi, but not over here. That's really important. Yeah. Okay. So we have these quantization of the allowed binding energies of the electron to the nucleus. Where did that quantization come from? That quantization came from solving the Schrodinger equation. It drops right out of solving the Schrodinger equation. How does that happen? Well, in differential equations, as you'll see, when you solve a differential equation, what you have to do to solve it so that it is adequately describes your physical situation is you have to often impose boundary conditions onto the problem. All right? And it's that imposition of boundary conditions that gives you that quantization, right? That's where it comes from mathematically. So in other words, remember one of those angles that I showed you, the phi angle? You can see it would run from 0 to 360 degrees. But you also know if you go 90 degrees beyond 360 degrees, right? Suppose you go to 450 degrees. Well, that should give you the same result as if you had phi equal 90, right? So what you have to do is you have to cut off your solution at 360 degrees. When you cut off that solution, well, then that gives you, in these differential equations, these quantization. That's physically where it comes from.